In this video, we will present our research on the statistical review of Greenville basketball. The contents will go from introduction, dataset characteristics, preliminary analysis, model building, diagnosis, and validation, and final model report and application. Because of increased data size and detail of data, many professional sports teams use their own data to achieve their goal more efficiently or enhance players' performance. The demand of analyzing data for a professional sports team will be higher and higher. From the chart, global sports analytic market was $1.9 billion in 2019 and will be $5.2 billion in 2025. The reason for the high demand is that there are many successful cases of adapting sports analytics. First, the most famous case is Oakland Athletics and Billy Beane. There is a movie called Moneyball which is about this case. They became the first team which won 20 consecutive wins in MLB by analyzing the data. Chicago Cubs won a World Series in 2016 in more than 100 years by using sports analytics. Also, Chicago Blackhawks won 3 Stanley Cups in 6 years by adapting the data analytics. As you can see, there are many successful cases in different sports. But how about the basketball? In basketball, there are a few successful cases of sports analytics. Luckily, we are able to find data of Greenville basketball team with having enough variables and data sets to analyze. Our research is to find that if there is any factor that affects the point differential. If so, what is the most important team statistics that determines the point differential?
The dataset contains data from 147 games from 1997 to 2006. The original dataset contained 20 variables, however some of the variables were not continuous, like an indicator, 1 or 0 if Grinnell won the game. These discrete variables were omitted from our analysis. Additionally, we omitted variables that were repetitive. For example, the points scored by each team is given, but since we chose the point differential to be our response variable, using both would be repetitive. The two variables would provide the same information. The variables we chose are outlined in the table on the left. X1 is the number of field goal attempts by Grinnell, and the range is 49 to 126. X2 is the total number of Grinnell rebounds, and the range is 21 to 71. X3 is the number of points scored in a game by Grinnell, and the range is 55 to 155. X4 is the number of assists Grinnell had in a game, and the range is from 2 to 36. X5 is the number of turnovers Grinnell gave up, and that ranges from 5 to 33. X6 is the number of blocks Grinnell had in the game, and that ranges from 0.9 to 13. X7 is the number of steals that Grinnell had in the game, which ranges from 3 to 29. Those 7 variables are all of our explanatory variables. Our response variable is the point differential for the game. This is Grinnell's score minus the opponent's score. The range is from -44 to 76.
I made a scatter plot to explore the relationship between the x variables. Afterward, I checked whether the correlation between these variables was statistically significant at an alpha level of 0.05 using a t-test. Finally, I used the R value to determine the strength of the correlations. The plots that showed statistically significant correlation are circled, with R values less than 0.5 in orange and greater than 0.5 in red. I determined there is a moderate correlation between X1, X2, X1, X3, and X3, X4 circled in red. There is a weak correlation in orange circled plots. Then I checked if each x variable is important to the model when other x variables are already in the model using added variable plots. None of the graphs are flat, showing that each predictor variable adds useful information. All plots show a linear relationship as well, showing that a linear term in xi may be a helpful addition. Next, I checked for impact of multicollinearity using VIF. The VIF results are all below 10, showing that although there is some correlation observed in previous analyses, VIF shows that there's not enough multicollinearity to affect the model. A residual plot of each x variable and fitted values were made. Most of the residual plots are flat and random. Slight curvature on the GRS and fitted value plots show that there may be an issue with constant variance.
Then, we checked if our model holds for the assumptions of constant variance and normality. We assume that the errors and hence the observations are independent since each observation is taken from a different basketball game. Moreover, to test for the constant variance, we did a Brown-Forsyth test, which has a null hypothesis that states that the errors have constant variance. The test gave a p-value greater than 0.05, which means that our data holds for the assumption. Then, we did a Shapiro test to test for normality of the observations. The null hypothesis here is that the errors follow a normal distribution. The p-value was smaller than 0.05, which means that this assumption does not hold and that we need to transform our response variable. To determine how to transform our response variable, we decided to use the Box-Cox procedure. It was decided that a log transformation would not work since the assumptions previously mentioned did not hold. The first step in our transformation was to add 45 to the response variable to ensure it contained only positive numbers in order for the procedure to work. As we can see from the graph and the code, the Box-Cox procedure suggested that we transform our response variable by raising it to the power of 0.758. For convenience, we decided to use a value of 0.75. All the assumptions hold for the new transformation of y. Moreover, the multiple r² and adjusted r² were higher for the new model, suggesting that the model can explain for more of the variability and is a better model than the one we previously had. Our next step in deciding our model was to search for outliers and influential points. From that diagnostic plot, it is suggested that a few observations could be either x or y outlying. To determine if there was an outlying y observation, we used the studentized deleted residual method. If the t-statistic of an observation was higher than the Bonferroni critical value, which is 3.7, then it would be considered outlying. None of the observations met this criteria. Then, to determine if there was an outlying x observation, we used the hat matrix leverage values. If the leverage value was higher than twice the mean leverage, which is 0.1, then it would be considered outlying. Observations 1158 and 125 met the criteria for X outlying. Moreover, from the diagnostic plot, we can see how influential a point is by the size of the circle that represents it. To determine if an observation has little, moderate, or major influence on the model, we use the Cook's distance method. None of the observations met the criteria for either a major or moderate influential point. Therefore, we decided that none of the observations would be considered an outlier or influential enough to affect the decision of our final model. We tested for a regression relation between our predictor variables and our response variable. The null hypothesis was that all betas were equal to 0. The p-value was smaller than 0.05, suggesting that there is a significant linear relationship between the response variable, point differential, and at least one of our predictor variables. Moreover, as we can see from the output, if we were to test if a specific beta is equal to 0, then it would be suggested that the number of assists and the number of blocks made by the team could be dropped from a model containing the other predictor variables. However, further analysis is needed at this point to confirm that that would be the best model or not.
Whenever we were trying to find our final model, and our initial problems were normality and using point differential being negative. Point differential is a y value, so we fixed our normality by doing y to the 0.75 power. However, we couldn't use our negative values to do the 0.75 power. So in order to fix that, we added 45 to make all of our values positive. We also found that keeping all of our x variables in the final model was very important. Two of them could have been dropped, but we decided to keep them in order to get a higher linear combination. And so our overall final model is point differential plus 45 to the 0.75 power. All 7 of the other factors are important to the final model. So now, how do we apply it? The overall goal of our research is to help Grinnell's basketball team win games. And by winning games, a win is a positive point differential. So we're trying to help them get a positive point differential. Using our research, we were trying to find which of the statistics help predict point differential. And our best predictor was Grinnell's points that they scored in the game. And we found that the worst predictors were Grinnell assists and Grinnell blocks in the game. While these two were the worst, they were kept in the model because they added value. And knowing these, the Grinnell basketball team can focus on certain aspects in the game, such as scoring points more than practicing assists and blocks. So because these factors add more value and can predict a higher point differential than the other statistics. And we believe that they should focus on scoring points in practice and in games.